So let us start by recalling what we saw in the previous video. So in this section we are linking graph theoretic notions with notions from linear algebra in a specific manner. So what we have seen so far is this. We have a graph G with vertex set V and edge set E, where V has n elements. There are n vertices in the graph, and the edge set E has m elements. M edges are there in the graph. What we then did, we defined something called the vertex space. We denoted it by nu of G, this is the vertex space of G, and what it is this. It is the vector space of all functions from V into F2, where F2 is this two element field consisting of a zero element and a unit element. And we already know what the vector space operations here are, but still let's just see them once more. So if we have two elements F and G in our space, what does it mean to add them? Because see, being in nu of G means each one of them is a function from V into F2. So their sum also is a function from V into F2. What specific function? That is defined like this. Vi, any element of V is some Vi. It is defined to be the F image of Vi plus the G image of Vi. And it makes sense also, because F of Vi and G of Vi are both going to be elements in F2. So it is their sum in F2. That means this addition is the addition we have in the field F2. Similarly, we have multiplication by a scalar. Say if you consider a scalar lambda in F2, which of course will either be 0 or 1, then you can define lambda f to be that function from V into F2 which maps Vi onto lambda times f of Vi. Because lambda is coming from F2, f of Vi will be an element in F2, so the product that we see here is the multiplication of lambda and f of Vi using the multiplication that we have in F2, the multiplication operation. Now it turns out, we have already seen this, that under these two operations, nu of G forms a vector space over the field F2. Then we saw more things, like one can set up a natural one-to-one correspondence between the elements in nu of G, which are of course functions like this, and the elements in the power set of V, or which sometimes is also denoted like this, 2 to the power p. They mean the same thing. It means the power set of V. And how that correspondence is set up is this. Each function in nu of G corresponds to a subset of V. That is, it corresponds to an element of V. What element? Namely, that element all of whose or to put it more clearly, this subset, this specific subset. That is the inverse image of 1 under the given function, because by definition the inverse image of 1 is going to be a subset of V, and it is in fact precisely the set of those points in V which are mapped by the function onto 1 and not 0. Okay, because a single point in V cannot be mapped onto both 0 and 1, it's the function. So f in nu of G corresponds to this subset, which is a subset of V, and as such it's an element in the power set of V. And conversely, if you have an element in the power set of V, that is the U, so that means, that just simply means that U is a subset of V, then this corresponds to the indicator function of U, which is just defined like this. The indicator function of U is a function from V into F2, whose definition is just this: 1U Vi, because after all we are having the domain equal to V, so I am taking Vi. This is equal to, this is defined to be equal to 1 if Vi belongs to U and 0 if Vi does not belong to U. So that's why it's the indicator function of U, because it indicates precisely which elements of V are in U, or precisely what U is. So either you say what U is directly, or you give this function, they are in fact the same thing. And you can also see that under this correspondence we are getting 1U from U, and in fact this inverse image is precisely U. So that is why this sets up a one-to-one correspondence between the power set of the vertex set and our space. Now under this correspondence, what happens to this vector addition is that it translates into, once you transition from your vertex space onto the power set of V, this addition translates into symmetric difference, because here in the power set of V we are dealing with subsets of V, so we can consider their symmetric difference, so it turns into symmetric difference. And the multiplication by scalar, that operation also turns into something which however is not something nice, like here we get the addition turning into symmetric difference, but the scalar multiplication also turns into something. And under these two operations, then the power set of V itself becomes a vector space which is isomorphic to the vertex space of G. And in this sense, sometimes we think of the elements in the vertex space of G as subsets of V under this isomorphism. What more we saw? We also saw this. Now that we have, or in fact we already saw these things, that there is an isomorphism between the actual vertex space, I mean the way we have defined it, and that power set version of it. Now that we have this isomorphism, we see that the vectors in our vertex space, so that means this itself now becomes the vertex space of G. Now what turns out to be the case in all these things is that the empty set becomes the zero vector. That is one thing. Then the additive inverse, that is the negative of each vector here, is the vector itself, I mean the set itself. So that just simply means that if you add a set with itself, where the addition is of course symmetric difference, then you get the additive identity. Something else also we have seen. We saw that this collection turns out to be a basis for the power set, I mean our vertex space interpreted in this way. It turns out to be the basis for this vector space, and we called it the standard basis, and as such the dimension of the vertex space of G is equal to n. Now all these things can also be done for the H set, and that's where now we start writing things formally. So the author writes, in the same way as above, the functions this time from the H set into our two element field. The field of course remains that same, form the H space which we are denoting like this, epsilon of G, the H space of G. And just like the vertex space, the H space is also isomorphic to the power set of the H set. In that sense, where again addition is symmetric difference, but now we are considering the subsets of the set of edges E, and multiplication by a scalar is similarly given by that isomorphism, where the elements are the subsets of E. So we are just simply going to repeat all the things we saw for the vertex space now for the H space. Vector addition amounts to symmetric difference the empty set considered as a subset of the H set is the zero vector and minus f is the same as f for all subsets f of E. In other words, for all elements f in the power set of E, the negative of any such element or the additive inverse of any such element is the element itself. So all these things were also true in case of the vertex space. So these are things we already know. Moreover, we also have the dimension thing. The dimension of the edge space of G is M. That is the cardinality of the set E, or number of edges in the graph. And now here is the thing. You see, although we have and we need the set of vertices in a graph, but when you think of a graph pictorially in your mind, what do you see? Basically, what do you think of? You actually think of the edges, in fact, not the vertices themselves. The edges carry the essential structure of the graph. So that's why we will be primarily interested in the edge space and not actually the vertex space. So the author writes, since the edges of a graph carry its essential structure, we shall mostly be concerned with the edge space. Now next comes one thing about which we discussed towards the end of the previous video. Now let f and f prime be two elements in the edge space of G. What does it mean? It means that f and f prime are subsets of E, or in the actual definition if we are really considering the actual definition of the edge space of G, then these are not subsets of E strictly speaking, but rather functions from E into F2. But we have already seen that correspondence is there, where subsets and their indicator functions are identified and are treated as the same thing. So that's why we can consider them to be subsets of E. Then we write a kind of product of these two space elements, that is these two vectors, where the notation will remind you of your usual inner product of two vectors, which is also known as the dot product in some context where we actually have them coming from real life. There we have dot product. You generalize that idea to inner product of a product between two vectors in a vector space. So just like that, we have this thing. Lambda m prime. But what are these things? where these are the coefficients of f in its expression as a linear combination of the basis vectors, that is basis vectors coming from our standard basis. Let me write one more element over F2, of course, because that's where the scalars are coming from, and lambda 1 prime, lambda 2 prime, these are the similar coefficients for f prime. So what is it? So that means we have considered two subsets of E, the H set of the graph, and we have formed a kind of inner product of them. Now these lambda 1, lambda 2 up to lambda m, these are the coefficients of f when you express f as a linear combination of the basis vectors. Keep in mind that because after all this is a vector space and this is a basis, every vector is a linear combination of the basis vectors with unique coefficients. These are things we already know from vector space theory. So when you express f as a linear combination of the basis vectors, you get these unique scalars. Existence of these scalars comes from the fact that the vectors in a basis span the space, and uniqueness of the scalars comes from the fact that these are linearly independent. All the vectors in a basis are linearly independent. So that's why we get these unique scalars. That's how, if you also express f prime as a linear combination of the basis vectors over your field f2, then you get another set of unique coefficients. And we are considering this expression. So you can see that after all, these all the lambda i's and lambda j primes, they are, or you can also say lambda I prime because I varies from 1 through m. All the lambda i's and lambda I primes are in fact field elements. So this combination of them is also a field element. So we are taking the product of two vectors and we are getting a scalar. So that's why I am saying it's like inner product, and it's also, it has been defined in that way. However, it is strictly speaking not an inner product. Why? That's because you only define an inner product on a vector space where the field is either the field of real numbers or the field of complex numbers, and this two element field is none of them. In fact, it is completely different from those two fields in one crucial aspect, in that those are fields of characteristic 0, whereas this has characteristic 2. In fact, its number of elements itself is 2. It is the smallest possible field. But anyway, so we now have this product. But there is another reason for this not exactly being the inner product, besides it being defined with this field. Besides that, there is another reason this does not quite behave like ordinary inner product. That's because you know that in case of ordinary inner product, this thing, if we have such a thing that say f is equal to f prime and this is not equal to 0, not equal to the 0 vector, then the inner product, I mean in the real case, if your vector space is a vector space over the field of real numbers or the field of complex numbers and you have your actual inner product, then in this case, that is an inner product like this is never 0. In fact, it is a real number that is greater than 0, and this helps you define a metric and such things. Okay, you already know these things. Here, however, that is not the case. Even if your two vectors are equal and none of them is 0, still the product can be 0. So in this respect, it is still differing from the ordinary inner product. Not only is it not the ordinary inner product due to the field being different from R and C, but it also does not behave like ordinary inner product. So that's what the author is saying next. Note that this being equal to 0 may hold even when not equal to 0. In fact, this product is equal to 0 if and only if there are an even number of edges common to f and f prime. Why? Why is that so? Let's see. This is just a passing remark made by the author, and in fact it's not very difficult to see why, but we have to see it once. Okay. So now what we are saying here is that this product is 0 if and only if f and f prime have an even number of edges common. Okay, it may have no edge in common. That number 0, that is no edge, that is also an even number. In that case this will be 0, but if say there are 2 edges common or 4 edges common, then also this will be 0. So let's see how. Okay, fine. Now if we actually think about expressing f, say, as a linear combination of the basis elements in the standard basis, what will it be? Let us consider the sets f and f prime, because they are subsets of the edge set of the graph. There will be edges in them. So these edges are those ei's only, some of them maybe. So say we have e, because we don't know which of the edges will be in f, so let me just write like this: ei2, eis, where s is of course less than or equal to m, the total number of edges, and this i1, i2, is, all these suffixes, all these subscript values are from 1 through m, some integers in between them. And say f prime is some such other things, ejt. F and f prime may not have the same number of elements, they may be different. Okay. Now when we are expressing f as a linear combination of the basis elements, what exactly will happen? You see, we have to think of f as really not different from its indicator function. So if we are really thinking in terms of indicator function, then we can in fact, for the sake of clarity also and in order to reduce confusion, let us consider 1f. 1f is the indicator function. So the indicator function, of course, will be this. Watch this carefully. ei2 plus eis. Why? That's because if you look at the right hand side, what do we have in the right hand side? We see that on the right hand side we have the coefficients 1, which I have written explicitly. We also have coefficients 0, which I have not written. Besides these coefficients, we see several other indicator functions of these singleton sets, which in fact are actually the standard basis elements. The standard basis elements, the way we generally write them, it only has these singleton subsets, but these subsets are under our isomorphism the same thing as their indicator functions. So I have written this whole thing as indicator functions. Okay, I mean in terms of indicator functions. And why is 1f equal to this? That's because now see, if you evaluate 1f, because it is after all a function, so you would evaluate 1f at what? At an edge in the graph. So say you have an edge in the graph. So this E is coming from your edge set, capital E. Now if this E is not one among these EIs, okay, EIKs say, then by the definition of this addition, you will do this I1 will be evaluated at E, because after all this is a function, plus the next one 1 times 1 ei2 will be evaluated at E, like this 1 eis will be evaluated at E. Now if this E is none of these things, none of these edges, then by the definition of these indicator functions, because that E is not an element in this set which is appearing as a suffix, this will be 0, this will be 0, this will be, all of them will be 0. But if this E turns out to be one of these EIs, say it is equal to ei1, then the others will be 0, but this will be equal to 1. So that means 1f is in fact equal to this function. Why? That is because E not being any of these EIs is equivalent to E not being in F. and hence correspondingly E being in F or E being equal to one of these EIs is equivalent to E being in F. So the right hand side is actually the indicator function of F, that is, this is equal to 1F. Okay, fine. Now let us go back to sets and not consider the indicator functions explicitly like this. So from this analysis, what we have come to know is this. When we are trying to express F as a linear combination of basis elements, it is just this. F is equal to plus 1 times E I2 plus 1 times E IS. Similarly, F prime is equal to 1 times EJ1 plus 1 times EJ2 etc. plus 1 times EJT. Now, according to our definition of that product between F and F prime, we have to take the sum of products of these coefficients. These are lambda 1, lambda 2 up to lambda m. These are lambda 1 prime, lambda 2 prime up to lambda m prime. But keep in mind that this EI1 may not be equal to EJ1 because I1 may be different from J1. Although actually we have all the basis elements in this expression. The ones that you don't see here have coefficient 0. So we in fact have all the lambdas. We in fact also have here all the lambda primes. So now when you consider these products, what do you think? Which terms would actually survive here as non-zero terms? Precisely those terms for which these things match. Say this EI1, say I1 is equal to 1, whereas J1 is equal to 2. Then here say, here say I1 does not appear at all in this sum. Then its coefficient is 0, so that 0 has to be multiplied with 1. So such terms will not survive in the sense that they will not be non-zero, they will be 0 and they will vanish. So only those terms will survive where the edges are the same. Any other types of terms, when they get multiplied because of this difference between the coefficients, if the edges are different, then the coefficients will be 1 of them will be 1, the other will be 0. So the product will be 0 and those type of terms would not survive here as non-zero terms. Only those terms will survive where the edges are common. So that is why you will get in fact here a number of ones. How many ones? As many edges you have common to both F and F prime. So this number is something, say K, then K is the number, or we can write it in short like this. K is the cardinality of the intersection of F and F prime. Now keep in mind that you are in F2, so this sum is in F2, and clearly this sum in F2 would be 0 if and only if K is an even number, because modulo 2. So that is why the product is 0 if and only if there are an even number of edges common to f and f prime. That's why this remark was made by the author. But despite this difference of this product from the usual inner product which we use very often, definitely this also has its own applications here. Now, based on this notion of this product, we can in fact similarly define this next thing. Given a subspace if this type of forms f of the H space of G, we can define this also you may recall from linear algebra. It is the space of all elements D in our H space such that the product of F and D is equal to 0 for all F belonging to our subspace F. And this turns out to itself be a subspace. This is again a subspace of the H space of G. I forgot its exact name. Is it called perpendicular complement or something like that? And in fact, it is the space of all vectors solving a certain system of linear equations. The space of all vectors solving a certain system of linear equations. The author asks which system of linear equations. And we also have this familiar thing from linear algebra. That same thing here also is true. Namely, the dimension of f plus the dimension of this thing is equal to the dimension of the H space, that is M. Now you can in fact understand precisely what this space is, and in fact why this is a vector space in the first place. That can be understood by considering these conditions. Note that because F is given to be a subspace of the edge space of the graph. So f itself is finite, so there are only finitely many elements in f. So using this fact, let's see actually what this system of equations will be that the author is talking about. The thing here is this: let our space F consist of these vectors. We don't really know how many of these F's will be there, but it is some number, say Fr. And each one of these things is what? Each one of them is actually a subset of E. Things can get pretty confusing, okay, so don't lose track of what these things actually are. Because we are in the edge space, each vector in the edge space is either a function from the set of edges into the field F2, or each such vector is a subset of the edge set E. Okay, so each one of them is a subset of the edge set E of the graph. Okay, now what we are going to do, we are going to consider the expressions that each one of them has as a linear combination of the standard basis. Say F1 has this expression lambda, because we already have a suffix, so let's put lambda 1 1 double suffix E1 lambda 1 2, and it will go like this: lambda 1 m E m. So this is the expression of F1 as a linear combination of basis elements. Let's write one more. F2 is lambda 2 1 E1 lambda 2 m E m, and it proceeds like this, and finally Fr is lambda R1 E1 Rm En. Okay, but we also have D, and that D is in fact an element in that F perpendicular. So that D itself is also some linear combination of the basis elements, but where we don't really know what D is, so our coefficients are going to be variable. x1 E1, we don't know means it will depend on what D actually is. These, however, are given fixed elements in the subspace F of the edge space. xm em. So the condition that these products are all equal to 0 for all f belonging to our subspace translates into what? It translates into a system of equations, and that comes directly from the definition of this product, precisely into this system of equations. Lambda 1 1 x1 plus lambda 1 m xm equal to 0. Why 0? That's because this that's because this is just the 0. And what 0 is this? This is the 0 element in the field F2. That's 0. Lambda 2 1 sum equal to 0, lambda r1 rmxn equal to 0. Okay, so that means what? That means D will be determined if you solve this system of equations for these xi's. Okay, so treating these xi's, these coefficients as variables, you get this system of equations, and solving them, each solution will give you one D, and each such D is in fact a solution to this system of equations. So that's why this space F perpendicular is corresponding to the solution space to this system of equations, system of linear equations, from which it can be easily understood that this is a vector space. And not just that, we can guess what the dimension of this solution space is, and this also comes from linear algebra. You see, as a system of linear equations, this has a rank, and that rank is what? The rank is the number of effective equations, or the number of linearly independent equations. Among these equations, if it happens that, say, one of them is a linear combination of the others in a non-trivial way, then of course that equation can be removed. That is because if you solve the rest, then whatever solutions you get automatically becomes a solution to the removed equation, or maybe there are a number of such equations which really can be disregarded simply because they do not add anything to these solutions or to the process of actually finding the solutions. So that is the rank. Technically speaking, you can also think of the rank like this. You treat these coefficients that you see here as giving you tuples, m tuples, which themselves are vectors in which space that is pretty evident. These are also vectors. Where in this space F2M, the space of all m tuples of field elements where the field is F2, and these vectors span a subspace of F2M. That subspace has some dimension, and that dimension is the number of effective equations, because the others can be removed due to the fact that the others are linear combinations of the ones that are not removed. And this dimension has a name. It's called the rank of this system. Okay, now keep in mind that after all, these vectors are representing these vectors only. These vectors are in our H space, whereas they are being represented in F2M using this basis and all these things. I mean, there you will set up an isomorphism between that subspace of F2M that these things span and F. So that is why the dimension of F is in fact equal to this rank. So that's how you have rank of this system equal to the dimension of F, and from linear algebra we know that the dimension of the solution space, that is the space of those vectors which solve all these equations, the dimension of that space is m minus rank. and the dimension of the solution space, because just like this space, the space spanned by these vectors is isomorphic to F, the solution space is isomorphic to the space of all D's, that is F perpendicular. So that's why the dimension of the solution space, that is the dimension of F perpendicular, is M minus rank, but rank is equal to the dimension of F. And that's how you have that relation, that if you add the dimension of F and it's perpendicular, I think it's called perpendicular complement. I may be saying the term wrong, okay. So if you add these two dimensions, then you get the dimension of the entire H space. So this is where I stop. We will continue with more notions like this, and in fact we are going to actually make, I mean, these things of course look very nice, but where are we going with these things? Are we going to prove something? Yes, and that thing will come in the next graph theory update, where we will see cycle space and how induced cycles span such spaces, things like that we will see. Finally, we will see that these are not just simply some games of associations and relations, but we do end up getting interesting results. So with that, I call it a night, and if you want to say something about these things, you can write in the comment section below, and my mail address will be there in the description. You can mail me also to share your thoughts about these things, positive, negative, anything. And tomorrow we are again going to solve Gallian's group theory problems. So that's just it for tonight. So see you tomorrow with Gallian's problems. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.